this problem says how many, or it says, should say how many kilojoules are required to fully vaporize 18 grams of water that is at 60.0 degrees Celsius. So first of all, we have to think about where we are at temperature-wise, and then where vaporization of water occurs. So the temperature that water vaporizes, or another word might be evaporates at, is 100 degrees Celsius, or 212 degrees Fahrenheit, which you might be more familiar with, but in science we always like the Celsius scale. So knowing that, we look at this problem and we say, okay, we're at 60 degrees Celsius, and for water to vaporize, we need to be at 100 degrees Celsius. So before we can calculate the heat energy required for the phase change to happen, we first have to calculate the heat energy needed to raise the temperature of the water from 60 degrees Celsius up to 100 degrees Celsius, and then once we're there, then we can calculate the energy needed for the water to vaporize or evaporate. So to know the total amount of energy, we're going to have to use two equations. The energy for this section of the graph, which is where the temperature is being raised from 60 to 100, we're going to use Q equals mc delta T. And then for this section of the graph, where the water is actually vaporizing, we need to use Q equals m delta H, because there's no temperature change associated with the phase change of vaporization, but there is a temperature change needed to raise the temperature of the water up to the vaporization or the boiling point of water. So we're going to first need to know the amount of energy to get from here to here, and then the amount of energy needed to get from here to the point of vaporization. And we want to know the total energy, so to get the total, we'll find each section individually and then add them together to get the total amount of heat energy. So let's start with this first part, Q equals m times C times delta T. And I'm actually going to get two different colors here so we can keep track a little bit more easily. So let's get a green pen and a purple pen. So this first section we'll use the purple pen for. Okay, so Q equals m times C times delta T. So in our problem, we're given a mass, 18 grams. So m would be 18 grams. C, so where would we get the specific heat capacity of water? Well, this is a value that we know. It's 4.184 joules per gram degree Celsius. Okay, and then the last part is delta T, or our change in temperature. So we want to start off at 60 degrees and end at 100 degrees. So our final temperature, we want to be at the boiling point, so 100 degrees Celsius, minus our initial temperature, we're starting off at 60 degrees Celsius. So 100 minus 60 degrees Celsius. And that will equal our Q for our first section of the graph. We might call this the purple section of the graph, where we're raising the temperature up to the boiling point. So 100 minus 60, that's going to give me 40 degrees Celsius is my temperature change. And if I look at my units canceling out, I notice I have grams canceling, degrees Celsius canceling, so I'm just going to be left with joules when I solve for my value of Q. And that does make sense. So let's do this. 18 times 4.184 times 40. And that gives me a value of Q of 3,012.48 joules. And I am going to keep that whole value. I'm not going to round because this is not my final answer. So I know that this is the first section of my graph. This is the Q for the first section, 3012.48 joules. And then I'm going to need to add it to the second section of my graph. So we'll do that part next. We'll do this in green. So this is where our phase change is happening. We've raised the temperature to 100 degrees Celsius to the boiling point. Now we just need to boil off the water. And to figure out how much energy is required for that, we're going to use Q equals M times delta H. And since the problem specifically says we're vaporizing, it's going to be our delta H of vaporization. This pen's not super dark, so I'm actually going to switch to my darker green pen. M times delta H of vaporization. Okay, so to find our Q, once again we use our mass, same mass of water. We still have 18 grams of water. But instead of doing C times delta T, we're going to go over to our handy-dandy formula sheet, and we're going to find the delta H of vaporization of water, which is 2260 joules per gram. So that's the second part, 2260 joules per gram. So looking at this, my grams are going to cancel out, one on top, one on bottom, and we're just going to be left with joules as our final unit. So let's put this in our calculator. 18 times 2260, which gives us 40680 joules, which is the second part of our energy needed to make this phase change happen. So we're going to add this 40680 joules. So this is the energy needed to raise the temperature. And this is the energy needed for the phase change. And so we want the total energy, so we're just going to add these together, and then I'm going to put my answer down here because I kind of ran out of room. I'm going to take these two values and add them together, and I got a final answer of 43692.48. And of course my answer is still in joules, so just carefully checking back on the problem, it doesn't want my answer in joules, we want our final answer in kilojoules, so we need to do some dimensional analysis here to get our answer to. Alright, so I'm going to push the paper up just a little bit here so we have some extra room to do our dimensional analysis. Take that 43692.48 joules. We're going to put joules on bottom and kilojoules on top, so the joules will cancel. Okay, kilojoule is the bigger unit, so our 1 goes on top, and 1,000 joules or base units in 1 kilojoule. So we're just going to divide our answer by 1,000, so move that decimal point 3 times, and we get 43.692. I'm going to stop there. So that's my value in kilojoules. And last but not least, we're just going to look at significant figures. Looking at our problem, we have 18, which has 2 sig figs, and 60.0, which has 3 sig figs. So we're going to round to 2 significant figures in our final answer. So we're going to keep the 4 and the 3. And we're going to look at the 6 to know whether we round that 3 up or keep it a 3. 6 is bigger than 5. So we're going to round up to 44 kilojoules, which is our final answer to this problem.